Okay, I want to just go over the process of linearization if you're asked to write the full linear system. Because as I was looking at the quizzes where you were asked to do this, a lot of people seem to be confused on what's involved in writing the entire linear system. Okay, so I know that a linear system is going to be something like that looks like this: u prime v prime equals a Jacobian times u times v. That is not writing the linear system. That is writing the generic formula for a linearized system. But if I want to write a linearized system for a particular equilibrium point, I need to be more specific. I need to specify what's u, what's v, and what's j. I need to describe all of these things more specifically and then plug into the formula. Okay, so let's just try that with this system. Okay, I have here x prime is f of xy, which is x squared minus xy. So I can factor out an x, and that gives me x times x minus y. And if y prime is g of xy, and that's y squared minus 2y, I can factor out a y, and that's y times y minus 2. So if x prime is equal to 0, and y prime is equal to 0, x prime will equal 0 if x equals 0, or x equals y. Y prime will equal 0 if y equals 0, or y equals 2. So let's sort of mix and match and see what our equilibrium points are. These are more specific, so I'm going to start with these. If y is 0, x could be 0, so I'll get 0, 0. If y is 0, x could be y, that would give me 0, 0 again. If y is 2, x could be 0, so 0, 2 will be an equilibrium point. Or x could be y, and that would make 2, 2 an equilibrium point. So there are going to be 3 different equilibrium points that we have for this particular system. So let's go about classifying them. So it is going to be useful, I think, to write the generic version of our Jacobian matrix. The Jacobian matrix is the partial of f with respect to x, partial of f with respect to y, partial of g with respect to x, partial of g with respect to y. So that would be 2x minus y, negative x, 0, 2y minus 2. So let's suppose I wanted to find the linearized system at 0, 0. Okay. Well, in that case, u will simply be x, because it would be x minus 0, and v would be y, because it would be y minus 0. Okay. And u prime v prime would be this matrix, but with 0, 0 plugged in. So that would be 0, 0, 0, negative 2 times uv. So the linearized system involves the differential equation. Now I could write it in matrix form, or if I preferred, I could write it as u prime equals 0, v prime equals 0u minus 2v. So I could write a system of equations, or I could write a single matrix equation, and then I'm also going to state what u and v are. All right, now if I wanted to classify this equilibrium point, I believe it's not going to work because this matrix is going to have 0 as an eigenvalue, but let's just confirm that really quickly. The characteristic equation would be lambda squared. The trace is negative 2, so minus the trace would be plus 2 lambda, but the determinant is 0. So the characteristic equation is lambda squared plus 2 lambda equals 0. That's lambda times lambda plus 2 equals 0. Lambda is 0 or negative 2. So we're not able to classify this particular equilibrium point, although we could write out the system. Let's try the others. If I wanted to look at 0, 2, then u would be x minus 0, and v would be y minus 2. And my system would be u prime v prime equals this matrix, but with 0, 2 plugged in. So I'd get 0 minus 2 is negative 2. I'd get 0, 0. Let's see, y is 2, so 2 times 2 is 4, minus 2 is 2 times u times v. So this is my linearized system. All of this that I have right here. Okay, that's not the same as writing u prime v prime equals j u v, and then somewhere else writing j is negative 2, 0, 0, 2. You're giving me the pieces, but you're expecting me to put them together. That's not what I'm asking you to do. I'm asking you to do it. That would be kind of like telling me, hey, I've got a line. It's y equals mx plus 5. Oh, and by the way, the slope is negative 3. You wouldn't give me a line of slope negative 3 that way. You'd actually plug in the negative 3. So I want to see the specific matrix with numeric entries in the differential equations. Okay, so for this one, let's go ahead and classify the equilibrium point. Let's see, my trace is 0, so I'm going to get lambda squared minus 0 lambda. My determinant is going to be negative 4 minus 0, so minus 4 equals 0. So lambda is going to be plus or minus 2. So I've got one positive and one negative real eigenvalue. This is going to be a saddle. So here the linearization worked, and we are able to classify this equilibrium point 0, 2 would be a saddle. So notice, it's incredibly helpful to have this generic version of J, the Jacobian matrix here, because we're using it. We've used it twice. We're going to use it once more in classifying this third point. But that doesn't actually show up as part of my answer, because my answer always involves a specific numeric matrix. Okay, so let's see if we can't classify 2, 2. So now u is x minus 2, and v is y minus 2. Again, we're always just translating it so that the equilibrium point, which is at 2, 2 in the xy system, will be at 0, 0 in the linearized system. And then we'll get u prime v prime equals. Now I'm plugging in 2 for x and for y. So I'm going to get 4 minus 2 is 2, negative 2, 0, 4 minus 2 is 2. So times uv. I got to complete the equation. Okay. All right, then my characteristic equation would be lambda squared. My trace is 4, so minus 4 lambda. And my determinant is 4 minus nothing, so plus 4 equals 0. So that's lambda minus 2 squared equals 0. So lambda would equal 2. So we just have one positive eigenvector. That's going to make this a source. Now, I don't know from this whether it's a source where in the linearized system I have just one independent eigenvector or I have multiple independent eigenvectors, but I do have enough information to classify that 2, 2 will be a source. So all I was trying to do was write the linearized system, which is everything that I've written from here to here, and then classify the equilibrium point. I've been able to do that at this point.